Get that screen up there. So you went to lunch, and the exciting conclusion was you're going to tell me which, if any, were extraneous. So let's go back to we actually found an extraneous on the first one. Whenever you get solutions with expressions with radicals, you try them out. And when we put 3 back into part A, we got -2 on one side and +2 on the other. That doesn't work. So we said that was extraneous. So there's an extraneous on number 3. And then, any luck on these? How about 2 and 3? Do they work? Why don't you take a second? 2. How about 2? Does 2 work? It fits okay. Not like there's a negative issue. -3 times 2 is, you gotta do under the radical first. Square root of 4 is 2. 4 plus 2 is 6. I get the left side is 6 and the right side is 2. So no, it doesn't work. So 2 is extraneous. So we got that. Extra. There we go. How about 3? The best thing about 3, all I have to do is put a little leg on it. Convenience. -9 and 10 is 1. Square root of 1 is 1. 4 plus 1 is 5, but that's 5 equals 3. What? 5 does not equal 3. What is the deal with this giving you wrong answers? You solved and give wrong answers. Well, the interesting thing about radicals is that it's interesting information and it's valid information. When you work with graphs in the imaginary world, there's some solutions that appear that in the imaginary plane that these would satisfy these solutions. So it's not like they're bad. It's just that they don't satisfy anything in the real world, the real number system. So that's kind of a fun aside. Now we get to dive into this fine set of problems. All that work you see right there, gone. All right, so go with me there. These, you're going to end up filling in all that with me. It's going to be awesome. Okay, how'd I do? Like my erasing? Looking good? You get a little bit more? Remember, if you ever want to come in from lunch or anything and you want to do the erasing, you just let me know. I'll hand it off. Here we go. It's like I'm playing Fruit Ninja. My kids play that. Do you guys play that? Okay. Ta-da! How are we going to deal with this? Well, it says solve. We could sit here and pick K's that work. It would be interesting. We could try it. Or we could do some algebraic stuff so that we could have a better time of finding K by itself. But it actually ends up being, there are 2 fractions. And it is almost, I'd say 98% of the time, a good idea to combine the fractions. Get a common denominator and add them. And then as you simplify, some reality will come out of it. It turns out this is a very contrived problem. It is no closer to the real world than, you know, the ghosts and Ghostbusters. This is made up by teachers purely for the sake of solving teacher problems. So when we get these solutions, it's a lesson to be learned, but it's a little bit contrived, I would say. Here's the thing. Remember when we did a common denominator before? In class, I was kind of giving you guys an introduction, but I want you to try this out. This is the general rule. You probably know how to add these fractions just fine. But imagine it's a over b plus c over d. Very general. Okay. If I were to add those, if you didn't know, the quickest way to a common denominator is the product of the denominators. So if you can't think of something, because I used to sit there and go, let's see, what's the common denominator between 3 and 12? And you'd have to think for a minute. Or what's the common denominator between 8 and 24? You'd usually try and find the least common denominator. Well, we don't need least. What always works is the product of the 2 denominators. That's a common multiple, or least common. You don't have to worry about least anymore. It's just a common multiple. So I'm going to multiply in this fraction and just to get a common denominator of b times d. So on the left fraction, I'd multiply d over d on the left side. And on the right side, it'd be b over b, because that's equal to 1. But the big thing is you are multiplying by a form of 1, so it doesn't change the value, it just changes the way it looks. And I think you're getting the idea that how things look, how you rearrange an expression, it helps you notice different things about it. Helps you make progress toward rewriting it or simplifying or solving, etc. After that, once there's a common denominator, you can add the numerators together. So those are my numerators over the singular denominator. So like 2/5 plus 7/5 is 9/5. You only add the numerators. You leave the denominator el mismo. So there's your lovely summed up fraction, two fractions added together. In the end, so this is what we've got. If you can imagine, I just said that a over b plus c over d is equal to AD plus BC over BD. There is a shortcut to this that is going to be very important as the problems get more complicated. No matter what fraction you add, it is this fast. Do you notice that we multiply the other, like each numerator by the other denominator? Because you had to do that to both sides. So it's like I multiplied the D times the A and the B times the C. And then the denominator is just going to be the product of the two. That ends up being the process. Any fractions you add, you just do opposite denominator times the numerator, opposite denominator times the other denominator. I don't know what I just said, but something. Yeah, an eighter. But over the product of the denominators. There's so many words in there with eighter. I'm going to write some like actual words that go with it that make sense. So when adding fractions, adding two fractions, which happens a lot, even in Calc 2 we actually have these scenarios where we're adding two very complex looking fractions, but it's not a big deal. You multiply by the other denominator and it's over the product of the denominators. Multiply by other denom and you set over the product. That is a big dealio. And if you have, at this point you're like, some of you are good at remembering things. This ends up being one of the big properties that we need for a lot of different tools along the way, even in trig as we go to next term. Set over the product. So don't forget this one. This is a good one. Okay. So there it is. Multiply by the other denominators. Set over the product of the denominators. We're going to use it for the one that we started with. This k minus 4 times 3. K minus 3 times 4. We're going to very liberally use our parentheses because there's a lot of errors that could happen with parentheses. But if you haven't written yet, join me now because we want to get this right. This shortcut is the whole point of these problem series here. So you see it ends up being 3 times k minus 4. The parentheses are really important. We got the whole 4 times k minus 3. And on the bottom, so I multiplied it by the other denominator in both cases with parentheses over the product of the denominators. So the denominators are k minus 3 and k plus 4 respectively. So here's my two denominators. Those I'll put underneath in parentheses, of course. Boom. Equal to, now right now I'm just kind of carrying along this equal sign. I'll put like quotations there. I didn't actually put it in there. I should probably not do that. It looks like a 11. But I would put that whole expression in there, the whole equal sign, and make it a full equation. That's it. That's the hard work. But knowing how to do that, the rest is distributing and combining like terms and all the algebra that you know how to do. So things, we have a little bit of work to do, but that gets you set up. No matter how messy your fractions are, you can add two fractions slick as can be. Other denominator times other numerator over the product of the denominators. Voila. And I did that little arrow diagram, and I think that helps. Now we can distribute algebra from here on out. 3k minus 12. And I distribute the 4 here. If these were, sometimes this is a negative or a minus, so you distribute a negative 4. Be careful. But it'll be minus 4k, or plus 4k. Almost tricked myself. Minus 12. And the denominator, you can distribute that out and get k squared minus 4k minus 3k plus 16. Now again, it's equal to that original expression. I'm just not writing it till the end. A lot of simplifying right now. So those are getting the sum of those two, and then after that it's just standard, hey, I gotta distribute, gotta combine like terms, all the normal stuff that happens. Pretty normal. Okay. Like terms, got them. Put some things together. Those are some like terms, here's some like terms. Just put them together. And what do you got? Do you know what it is? Put them together and what do you got? Bibbidi bobbidi boo. Salagazula Menchikaboolaroo. Do you guys not know that at all? Is it that past? It's a Disney song. You do know. Yes. Put them together and what have you got? Bibbidi bobbidi boo. Salagazula Menchikaboolaroo. When I'm doing mundane mathematics, it helps to sing Disney songs. There it is. Like adding. Adding I consider mundane. Everything else is cool. Don't like adding and subtracting. Not my favorite. Okay. And that is why I'm not in accounting. Ugh. Okay, here it is. That's it. Now, this time I wrote the original. I wasn't, this is the original expression on the right-hand side. So, think of where we came from. I took the very first equation. I'm going to circle it in a purple highlighter. Here's the original. I simplified the left-hand side, and now it looks like this. The right-hand side I didn't touch. So, and because I added the fractions. Today's new big to-do is, how do I add two crazy-looking fractions? And it's multiply by the other denominator, use parentheses, over the product in the denominators. Do a little simplifying, you're good to go. Now, at this stage, this is where it's all contrived, made up by teachers in their massive free time. That problem right there worked out really nicely, and real problems in the real world don't work out nicely. But that one, do you have any idea? One, can you solve it just right now? Two, do you have any ideas on how to maybe simplify a little and then solve it? What do you think? Any insight on this one? You guys got some clever tricks? I just like some. You even know what the k happens to be? Solving would be to find k. Yeah, what do you got?
Multiply by k squared minus 7k plus 16.
Multiply both sides by the denominator. That is like the way.
It's supposed to be a 12, not 16.
Yeah.
4 times 3.
4 times 3 is 12.
You guys have been whispering about that for like 5 minutes. You're finally telling me? I heard the whispering. I didn't know you were going to. You're too nice. Of course I'm not going to notice that. I don't notice anything. Is it minus 12?
I know it's plus 12.
Yeah. 12. And then look, I even wrote the 25 over the other one because I knew I wanted them to be the same. I morphed that one just to fit my needs. Again, it's contrived. It's all part of my evil plan. You ready? So wait, that's part of it. Okay, and what? Now, Claire, was it just that you were pointing out, or did you have another idea? That's it. Okay, just to humor me. Got it. Okay, good. Multiply both sides by the denominator. Good. That's like how we deal with these, and I'm glad you pointed that out. When it comes to solving equations with fractions on both sides, that tends to be, we don't like the fractions, so we multiply by the denominator. That actually, in the non-clean world of solving, is what usually happens. You're so right. We could do that. They would cancel, and what would be left? Just that on top. You wouldn't have a kind of a different perspective on how you'd solve this one? Or could just tell me what k happens to be? That one? That'd be cool. Just undo this for a minute. Think of something. I don't know. What else kind of jumps out at you? Guess a k. Give me a k. 7. Yeah. How do you know it's 7?
I just know.
You just know. Mm-hmm. That's a very mathy person answer. I just know. Why?
Well, you said that the denominators cancel out, so 24 plus 25 is 49 divided by 77.
Okay, that makes sense then. Yeah, very nice. Do you know I think, if you think of, the denominators cancel out, do I even need to look at them? If two things are equal to each other, one side equal to the other, I'm asking, in a sense, in an equation, how can I make these the same on both sides? Or, in other words, hey, I got 25 in the numerator on this side. What can I do to make this one have the same numerator, 25? I don't even have to look at the denominators. They already match. So if you have matching denominators on both sides, you can multiply both sides to cancel them. Or once you know they're the same, you can ignore them. So when you're doing an equation like this, the idea is, what do I need to make them equal? denominator